and thus it is natural to take but here we want to have non-standard ones that are spiral or square space filling curves that are non-crossing and fill a section. Here though, that we're mostly only interested in curves that are defining classical functions or plane curves that only define that are nowhere space filling. Say. Thus, it is natural to take the point of view of analysis and require differentiability in addition to continuity. Well, so you need stronger conditions than that. You need they're not space filling, because the differentiability is not necessarily a feature, not part of non-standard space filling curves. Which is kind of along the lines of, like, can you even draw a line mathematically? It's like, well, you're going to need a non-standard development to make an Aristotle's continuum like that. And it's involved. Thus, it is natural, but still this assumption is not quite the right one. Differentiability of a map just means it can be linearly approximated. Differentiability of a map, it depends on the definition of differentiability. So it's not necessarily so that something that's differentiable is linear. For example, when you have the circle and either edge, its gradient is undefined. It's nonlinear, but it still has what exists for it. And in transformation coordinates, then that would be linear. But here, we can kind of read off differentiability of a map. And when he says just means that, it's rather that differentiability of a map it's non-standard, not that it cannot be linearly approximated. For the image set, however, this no longer needs to be the case. The image set. From a geometrical point of view, it makes sense to require that the image curve can be approximated by a line at each point, i.e. to require that the image curve has a tangent as a geometrical linearization at every point. Yes, that seems fair, insofar as it has a defined tangent and normal, right angles and straight lines. Whereas in the infinitesimally small, there's either right angles and straight lines in the metric and the triangle rule and tangents and normals, or an analytical basis of a line segment, where the abstract curvature, this continuous origin that's being developed, is having several models, kind of like the infinity we were just talking about. From a geometrical point of view, it makes sense. This means that the derivative of the map from I to Rn must be non-vanishing. Well, I'm going to call this a property, a map with this property, an immersion. This simply means that the derivative of the parametrization always has the highest possible rank, which in our case, where the domain is an interval, is 1. Definition. A regular parametrized curve is a continuously differentiable immersion C from I to Rn defined on an interval I. This means that C dot equals dC over dt is not equal to 0, holds everywhere. Aha. Now, when in the earlier talks, then this was already introduced, and it's kind of the opposite idea of, or it's an extension of the idea that there are no asymptotes in differentiable curves because its value would be infinity. Here they're also and here we're leaving out 0 too. And so this curve for this differential geometry is a bit the wicket then, because then that makes it so it can define the tangent, and then also makes it so it can define the normal everywhere, because in nowhere will the tangent nor the normal be infinity or 0. It's called the tangent vector to C at t naught, and the line spanned by this vector through C t naught is called the tangent line to C at this point. This is a geometric point approximation of the first order in a neighborhood of the point with C at t naught plus t equals C t naught plus t dot C naught t naught plus O t. So then you can make linear approximations very readily. A regular curve is an equivalence class of regular parametrized curves where the equivalence relation is given by regular orientation preserving parameter transformations. So when it says orientation preserving, these transformations phi of that take a alpha beta to ab, where phi prime greater than 0, where phi are bijective and continuously differentiable. So that's just functional composition of sort. C and C compose G, or C compose F, are then considered to be equivalent. Of these regular curves, the length of the curve integral from A to B of the line integral of dc over dt is invariant under the parameter transformations as just described. Hence, one can view a curve as the motion of the particle with the trajectory of the particle as a function of time. And I hope it'll be using the word trajectory the same as it's also already defined. Because so far, curve is defined as a subset of what are curves. Whereas usually, as time goes on, something like a curve or a function is defined as a superset of the previous definitions. So for example, when the functions began be described as Cartesian, many classical functions, like these Cartesian functions, are not classical functions. They're not functions. So at some point in time, it became so that that everyone's expectations of what to expect made it so that we are going to now call our old-fashioned functions classical, and our new functions, our Cartesian functions, just plain functions. And so here, it's kind of the reverse, because some of this is what is a curve, and is similar. The curve had to be, curve was just any form, and then it had to be a form that made by not lifting the pencil while drawing on the paper. And for example, maybe not crossing, or otherwise planar or so. And then it became something that had to be definable in terms of coordinates, which arbitrarily everything is, whether it's in terms of kind of like the compass and edge, or the third geometer's tool, an Archimedean spiral, or something like that, in terms of classical constructions to make these curves. Here's an example where to then enable this whole body, as we've been talking about, of this differential geometry, which before was like, there are too many pathologies, what are considered pathologies in this work, for us to do our work, which is this sort of brain dead ability to make these linear models and nets out of whatever we're left with. Because as long as we don't have to care about these special cases, then all this other stuff becomes kind of justified. And so these immersions are like, these curves are very particular curves that don't admit otherwise. These kinds of cases that our definition of differential is also a little bit skewed. And so that then because our definition of differentiable is basically linear. And so then for this differential geometry and these immersions and submersions, it provides a field then say, and so you'll have to unlearn some of your either have to unlearn or never learn this other way it was called original and correct, it's correct, and or if you know that and you actually need to employ that in its own context where it lives, then it's up to you to separate and make all the bridge results where these equivalence classes hold for these theorems, that these equivalence classes do not hold for these other theorems, and anything you'll have to do that involves taking the limits or anything about it that makes so only courtesy properties that are so about these restrictions, that they're taken away and put back together again by these other bridge results or transfer results. So that leads to being kind of cumbersome, awkward, and fraught with possible ambiguities in terms of our desiderata, what is sensible, fungible, and tractable, and having a common definitions for everything. And then the specific, that these are like DG curves, differential geometry curves, or these are linearly approximable as linearly approximately differentiable, instead of what we'd otherwise just say differentiable. Or, and according to geometry, there exists a tangent, which to any curve in geometry, there exists a tangent at any point. It's just a straight line that's coincident with the point. And on a curve with that's not a line, only with that point. That also is that it's in a continuous range of tangents, that it would be a continuous, it would be in the same order as a continuous translation of the course of passage of a point along that curve. Its tangents, that its tangents all build each other for a continuous domain. So you can see it why, in this sense, it's easy and nice to have like the definition of the point set continuity, but you really need to attach a topology to it, this continuous domain, and have a point topology to define something like this continuous curve and the continuous space of its tangents is existing in that space. So this is why it's important to be able to understand what complementary duals are and what a dialectic is and how things need to be put together, because otherwise this, and you know, when I said insensate or whatever, and that this theory was thus its restrictions make it incapable or unsuitable for some other things that are irrelevant, just make it so that those would be viewed in a positive light, that the idea fixed here is that there are no curves that aren't so defined, which is a restriction of comprehension, and thusly all this other general method is always applicable. And so at the end of the day, we'll be able to just work on it symbolically until we get stuck, and then throw it at the computer and it will crunch out the bits, which is a very great thing if you need to actually get numbers out of something and don't have all the time to be the analyst and the geometer. It's just not necessarily closed and complete, so there's more to it than that. All right, so that is, again, just that's very fundamental in the differential geometry. And so we've got to that in the old-fashioned way, that the plane curves have integral equations, and then in the new-fashioned way that the differential functions have solutions, and then that in this differentiable geometry way that the immersions and submersions don't have all the curves, and instead of not just having infinity, like the usual new way does for curves, they also don't have zero. So that then they can always have a non-zero and non-infinite tangent and normal, which is a very useful property. Tangent and normal are always orthogonal to each other. And so if one or the other is zero, the other one is infinite. It's derivative, that is to say. And so when neither are, then you can always have all kinds of algebraic applications about them without having to care or think about their indeterminate forms. And then here there's that, basically the old school approach seems to have some more of this developed. There's another similar book from this mathematical texts. It's about topology, and it says it's now included in honors courses in mathematics in most universities. Yes, it is. Continuity on the Euclidean line. Let's see what he says about continuity briefly. Because continuity, this is all continuum mechanics. This is all geometry and continuum mechanics arising from classical constructions and line drawing and this. A convenient way of describing continuity is to increase the idea of a neighborhood. And the neighborhood is all the points in delta epsilon x in the region for what delta epsilon x holds true. That this is usual notion of the open and closed sets and the usual open topology. There are multiple topologies. There are multiple definitions of topology, and the properties of topology are what make for that these neighborhoods basically have the critical points, and that the critical points are limit points in terms of that, are just as was discussed when you have a range of motion. So the whole idea of motion is kind of a secondary thing, but it's almost inextricable from the existence of a topology. Because the existence of a topology means that you can make as arguments as over these neighborhoods that things that move as about them in some framework that holds them all together, that they're continuous translations. And we call that the course of passage of ordinals, why there's an integer continuum, 0 to infinity, and then these points, it's called motion. That geometry is in the sense motion. Continuity in the Euclidean plane, and that continuity thus reflects that it's that motion there's an ordering of the points, and so motion goes through the ordering in the normal ordering. And then there's also the attachment with this with time or uniform motion, that there's as of an interval of time, and a uniform motion basically is infinitely divisible in that any particular division of that or partition of that in terms of another partition same size sees the same rate in this and that. And then the whole space-time thing and space contraction or length dilation or length contraction plus time dilation together involves transforms in that still preserve this property of continuity overall. That it's all continuum mechanics. So that's to very much distill and make a digest of the properties of continuity that go into mappings, morphisms, or the shapes of things together, in topological spaces, that a space, then for a vector space, is a topological space. Here he talks about the Kuratowski space. A set, in a Kuratowski space, let a set be called closed if it coincides with its own closure. Then let a set be called open if its complement is closed. The systems of open sets defined in this way forms a topology. So we'll look to Kuratowski a bit later about topology, because it ends up then these become several things: the theory of functions, the theory of topology, the theory of geometry, theory of numbers and sets and parts and arithmetic and geometry. Here there's even talk about the deconstructive account that takes addition and division as the two operations of arithmetic as into two different parts that then compose back together, and their gestalt make the real number line. Integral curves, chapter 3, equations of higher degree. Now, I'm not yet too interested in the equations of higher degree than 1, because all I'm interested still in is in the positive numbers to the positive numbers, including or not including 0 in case it's singular or missing, or present or vacuous or trivial, and mostly continuous functions in that. And so then when I get to thinking about higher order differentiable curves that have the plane curves in that with higher order surfaces, is that we do have the equations of higher order. So let's see what it says about the general integral. When the primitive is of the form f of xy constant equals 0, involving the arbitrary constant c implicitly, the differential equation will arise through elimination of c, the constant between the equations. F equals 0, df over dx, or partial df dx plus partial df dy, y prime, equals 0. So this is introducing the partials. And so before there was this talk about the gradient and the level lines and stuff like that. It's like, well, how do we compute the differential of these surface equations when we have a surface in x and y, and we want to find how it changes with respect to z, and specifically what direction it's changing the most, or the steepest descent, the gradient. And so here he's just saying that when the primitive is a form of having a constant, fxy constant equals 0, then we can get this differential. So this is kind of like, you know, when I said that in my theory it was insensate to some of these other things because it has it's restricted to x equals y, defining functions about that, symmetrical about that, and also in terms of ceiling of 1 over x that then is used to scale that out and build an infinite series of functions that make for having infinite series of coefficients to make a series for those. And then in the differential geometry, it's like, well, these curves have their normals and tangents are neither 0 nor infinity, instead of the usual just that they're not infinity. And then here it's just saying, well, some of these equations of higher degree, when the partials make sense is the sum of the partials makes sense for the Laplacians and all these things, specifically when there's no constant term interactions, or what you might call it, about this thing. So that implicitly it drops out. These implicits are what make for the vacuous and trivial that otherwise would be outlier cases, either something that can't be derived or something that can be derived, whether the implicits are present or erased. Only in exceptional cases will the result of this elimination involve y prime to the first degree. And he'll be curious if he introduces what these are. If the resulting equation f x y y prime equals 0 is a polynomial on y prime, involving y prime to the nth power, it is said to be of degree m, but it may be irrational in y prime or even transcendental. This gets into that otherwise it would be that's the usual extension of after rational, but it gets into, for example, solving polynomials of well, monomials are simple, they're linear, and in terms of binomials with the second power, trinomials and third power, or the cubics and quartics and quintics, that there's a theorem called Ruffini-Abel, and it says that then it gets involved how to develop those. Theoretically, fxy prime equals 0 may be solved for y prime, giving a set of equations, and then this gets into the usual approach from this integral equation, calling that a differential equation and finding its solutions. So in the old school way, what we call differential equations were called the integral equations and general integrals. And then their treatments often involve what would today be considered algebraic manipulations of the differential, which are argued as either too easy or too easy to get wrong. This set may be finite, or in the case of a transcendental equation, infinite in number. So when it expresses that there's an infinite family of solutions, that's basically the difference he has, that is transcendental, that there's an infinite family of solutions. If the general integrals of the equations are respectively f(x,y,c) equals 0, f(1,x,y,c) equals 0, f(2,x,y,c) equals 0, the general integral of 18.1 is defined to be any equation f(x,y,c) equals 0, which is satisfied when and only when at least one equation, 18.3, is satisfied. In particular, when the equation is of degree m, its general integral will be the product of the m integrals, that is, it's a product of the integrals. What do you think? f(1, xyc, f(2, xyc, fm, xyc) equals 0. So that's interesting to think that a product of the integrals would equal 0, because either one of them is 0, or otherwise that these functions result that the solutions make for it so that it's a polynomial, for example, and then its roots. That take them, excuse me, taking the product is as of additive terms as for the additive identity, which is 0, when in terms of otherwise it's only the multiplicative annihilator that's 0. In practice, however, the decompositions into da-da-da and the solution of these latter equations or both may present difficulties, in which case other lines of approach, some of which will be indicated in the following sections, may be attempted. So here it gets into the usual notion of the differential geometry, is that there's lots of different things going on when in terms of a checklist of means to approach for different kinds of curves with different kinds of properties and different kinds of functions and different kinds of integrals and derivatives, and the continuity of the conditions and the spaces they're in, and the topologies is about them, which vary in some models, all these things, and those that come together making for differential analysis and the methods and analysis in the differential. Errors in writing and printing are apt to arise through confusion between y prime and y. Oh, these are obviated by writing p for y prime, a convention that will be adhered to throughout the present chapter. Example 1, let the primitive be the equation of a one-parameter family of straight lines. So here, my one-parameter family of straight lines is y equals x. If the gradient m of each straight line be taken to serve as its parameter, the equation may be written as y equals mx plus fm, where f is some specified function. So here it's y equals m equals 1, and f of 1 equals 0. Then p equals y prime equals m. Yeah, it's constant. Eliminating m, we obtain the differential equation y equals px, which is just y equals x, plus f of p, which is 1, which is 0. In particular, the equation of the family y equals mx plus a over m, where a is a constant, is the equation of the family y equals mx plus a over m, so plus a, so any offset of the identity function by a, its intercept, instead of the origin, where a is a constant, is y equals px plus a over p, so that's just y equals x plus a, or p squared x minus py plus a equals 0 of the second degree. But here again, that's just x minus y plus a equals 0, or x plus a equals y, or y equals x plus a. So it's interesting just to carry out through these, it's sort of a check just to see that whereas this higher order approach makes for so, then what I'm curious about is then there's this tension in the middle. There's this tenuous that's held up that makes it so that then we can think about how this paraboloid and this approach about the differential and the solution and where this plane curve, the line, is having solutions and of things, and when and where it becomes kind of the edge of things, of a space in a higher or lower dimension, that's all that surfaces is just this line. That then it becomes usually that would be something like, well, that's entirely contrived, it can only be the astable solution. But at the same time, when you get to continuous solutions and their optimizations, you can always apply a continuous arbitrary mapping to that makes that the shortest line, the shortest straight line, this difference between one-dimensional and two-dimensional, in a sense. And the idea is if it can be held up so that somehow tense, or that's tenuous is that it holds together, and like tentative is that it kind of barely connects, and tenuous it is kind of barely holding itself together. It's still that in mathematics that can be the solution, which is very nice. Example, p squared minus 2px plus x squared minus y squared equals 0. So here it's just x squared equals y squared because x equals y. And this equation of the second degree may be decomposed into p minus y minus x equals 0 and p plus y minus x equals 0. So kind of like when we're talking about the very, very beginning of this implicits about the thing, when you say, well, what's the implicit? It's like there's a constant involved, it's a translation. Well, then the implicit here is about x equals y, and when you put in these other concepts of restrictions on the range of the domain of the function that make it so that it can hold up, the implicits has got a lot going on. And so implicits can include both things that can cancel and the things that will be totally, utterly contrived. And then that in terms of otherwise the parameterization of the systems, it reparameterizes all the things. Yet it can still be written symbolically and then treated like a constant. It's kind of like these quantization that has been talked about and these kinds of things. These are linear equations where general integrals may be written. And then this amused me. Y minus c e to the x plus 1 equals 0. That the constant is of this implicit constant, instead of writing the constant as just a scalar, now the constant is as of by an exponent times x. So this gets into these operator calculuses, it gets into these transformations on space, it gets into these continuous transformations, how to make it possible that, for example, when we see that multiplying, we obtain the general integral of the given equation, c squared minus c of the quantity e to the x, y minus x plus 1, or e to the x plus e to the negative x plus y plus 1 squared minus x squared equals 0. And so that's very remarkable. When you see e to the x plus e to the negative x, that starts to become very familiar as the basis of the kernel of the Fourier analysis that we were just talking about. And also other expansions, when those together in terms of those constants as of on those make that the constants as coefficients sort of as to establish the range, what established according to these scales, the most and least insignificant, that it could be a pretty interesting thing. Then he reads the Clairaut equation, Clairaut, C-L-A-R-A-U-T, Clairaut. We consider the equation obtained in the last section, y equals px plus f of p, or here that was just like y equals x, known as the Clairaut equation, with a view to discovering whether or not it admits of any integral other than the primitive from which it was derived. So here the integral is x squared over 2. This equation may be satisfied in just two ways. On the one hand, we may take dp or dx equals 0. No, because dp over dx equals 1. Whence p equals c, and thus recover the primitive y equals cx plus fc. On the other hand, the equation is satisfied if x equals negative f prime p, and if x is now eliminated, y equals negative p f prime p plus fp plus ... Equations were taken together are the parametric equations of an integral curve. By eliminating p, we obtain the equation of this curve in a form phi xy equals 0 involving no arbitrary constant. This integral curve represents a singular solution of the equation. Since the envelope of the primitive family is obtained by eliminating c between that equation and x plus f prime c equals 0, that f prime of c must be equal to negative x. And since the result of this, which is also negative y, and since the result of this elimination is identical to have eliminated p between it follows that the singular solution may be interpreted geometrically as the envelope of the family of integral curves. But here there's just x squared over 2. Example, y equals px plus a over p. So here that's just y equals, that p equals 1, and a is equal to 0. Differentiating, p equals p plus x minus a over p squared dp over dx. Firstly, dp over dx equals 0 or p equals c. Here it's 1. So it's that's so y equals c, which is 1, x plus a, which is 0 over c. Secondly, the alternative, x equals a over p squared, leads to y equals 2a over p, which is y equals 0, which is not true. Whence eliminating p, y squared equals 4ax. And so replacing that back, that would have to have replaced back within it something like 2a over p to make it so that, because a is 0, so it has to be divided out of both sides. So y times 2 over p equals 4ax. So then that y equals y squared equals x. So this is where it's interesting, because instead of the y prime being x squared over 2, it's that x equals y squared over 2. And it's just because the way this development is worked out, that it's built up as after, about, and this and that, that for this particular plane curve, it's kind of a funny thing. And so it gets back into this discussion as from yesterday. It's like, well, if we start treating this identity function as the actual axis of out of our origin, and so that, well, then the x and y axis are just kind of considered negative one-dimensional or half-dimensional, say, that together and we'll just talk about only the positive numbers here, and we'll call it rays, and we'll say that they're semi-dimensional x and semi-dimensional y. But here it's interesting that it kind of makes these alternations and reflections add up, and because instead of the y prime equals x squared over 2, that is kind of like that p equals y squared over 2, given that implicit is all plugged in. So it's just kind of amusing, and it's not very sensible, fungible, or tractable yet, because you need a lot of existence and uniqueness theorems, and then all sorts of completeness theorems for all sorts of limit theorems for any of these kinds of things to add up in these spaces, to make it so that you can pretty much analytically prove that then some of these kinds of results make for a Clairaut equation about this semi-dimensional original Clairaut's reciprocal or reflective equation that then is possible to solve for one in terms of the other, and solve differential equations in some senses a manner that reflect this notion of the integration that was kind of defined, which was what? Well, if you can define it as that the integrable region is under 1 over x, and so all you have to well, how can that add up like rectangles or rectangles? It's like, well, you just add up the square under 1, 1, and then you compute the one arm, and you compute the other, and you don't have to compute the other arm because it's symmetrical, so they're the same. And then the idea is to add those up and have those be the things. The parabola itself is an integral curve separating these two regions. Regarded as a quadratic in P, it has real roots only when y squared minus 4ax greater than or equal to 0, i.e. outside the parabola there are integral curves, the tangents, inside there are none. That's pretty interesting. So yeah, I'm carrying on with this idea about figuring out systems of implicits and explicits, which makes for how to work up some more of these ideas that make it so that instead of, and besides, learning the higher level differential analysis, so that it becomes intuitive and instinctual how to address geometrically, which is most intuitive and instinctual, these things that we have to address, even stuff like, what about continuous uniform motion? It's like, well, mathematics forgot that a long, long time ago because that way they don't have to remember it and can crunch things in easy as point sets, and from simple handy definitions of elementary objects, these fundamental theorems in these higher theories that result make things tractable to analysis and input to the tooling. All right. Well, what about continuous motion? It's like, well, you have to make your own. Okay. And so the idea is to figure out how to make this kind of original analysis and to build the non-standard stuff into it. And then up above say, okay, we're going to have our fundamental theorems, but these are restrictions of comprehension, and here's how and why. And we will certainly be able to make do with that, but these go into the things. And those are already what are called conditions and boundaries, you know, and this kind of thing. So on it'll go. Well, that's what for today. Hey, have a great day. Infinity. Have a great day.